This lecture is on buffer problems, specifically on preparation of a buffer solution. As you know, buffer solutions must consist of either a weak acid and its conjugate base, or a weak base and its conjugate acid. One can determine the behavior of a buffer solution by using the Henderson-Hasselbalch equation, and by using the pK of the weak acid and the desired pH, one can determine the amount of acid and base needed to prepare and make the appropriate buffer solution. The Henderson-Hasselbalch equation is pH equals pK plus log of the concentration ratio between base A minus over acid HA. The way we will tackle implementing this equation is in two parts. Part 1, buffer preparation involving a weak acid or base and its conjugate salt. This example involves preparing a buffer solution containing a weak acid and its conjugate pair. Additionally, unless specified, assumed substances are in solid state. If it's liquid, the density would be given, and if in aqueous solution, its concentration would be provided. The question is, suppose I want to prepare a pH equals 3.50 buffer solution containing lactic acid and sodium lactate. What mass of each salt is needed to make 1 L of a buffer solution whose pH equals 3.50? For starters, it would help to know the molar masses of the two salts. Molar mass of lactic acid equals 90.08 grams per mole. Molar mass of sodium lactate equals 112.06 grams per mole. K equals 1.4 times 10 to the minus 4. And pK equals 3.85 for lactic acid. The solution is that the ratio between base over acid is 0.446. Now we can rearrange, since the volume is similar. Concentration of A minus equals 0.446 times the concentration of HA, but will be expressed as moles. Since the volume of the solution will be similar, the desired molarity of the buffer solution is 1.00 m. Total moles equal 1.00 moles. This means that moles base plus moles acid equals 1.00 mole. If we sub moles base with 0.446 moles acid and solve for moles acid, it equals 0.6915 moles, and therefore moles base equals 0.308 moles. Now, solving for the mass in grams of each substance, for lactic acid, it is 62.3 grams. For sodium lactate, it is 34.5 grams. Therefore, one will need 62.3 grams of lactic acid and mix with 34.5 grams of sodium lactate in 1 L of solution to be filled to volume with water. This example involves a weak base and its conjugate pair. The question is, suppose I want to prepare a pH equals 9.50 buffer solution containing aqueous ammonia, 1 m, and ammonium chloride. What volume of ammonia and mass of ammonium chloride is needed to make 1 L of a buffer solution whose pH equals 9.50? Molarity of ammonia equals 1.00 mole per liter. Molar mass of ammonium chloride equals 52.49 grams per mole. Kb equals 1.8 times 10 to the minus 5. pKb equals 4.74 for ammonia, and pK equals 9.26 for ammonium ion. The solution is that the ratio between base over acid is 1.73. Now we can rearrange since the volume is similar. Concentration of A minus equals 1.73 times the concentration of HA, but will be expressed as moles. Like before, total moles equals 1.00 moles, and since the desired molarity is 1.00 m, total moles equals 1.00 mole. This means that moles base plus moles acid equals 1.00 mole. If we sub moles base with 1.73 moles acid and solve for moles acid, it equals 0.366 moles, and therefore moles base equals 0.633 moles. Now, solving for the mass in grams of ammonium chloride and the volume of ammonia, it is as follows. For ammonia, it is 0.633 L or 633 ml. For ammonium chloride, it is 19.6 grams. Therefore, one will need 0.633 L or 633 ml of 1.00 m ammonia with 19.6 G of ammonium chloride to be filled to a final volume of 1 L with water. Part 2, buffer preparation. Weak acid or base with HCl or NaOH to form conjugate salt. This example involves a weak acid and the addition of a strong base to prepare the specific buffer solution. The question is, suppose I want to prepare a pH equals 4.50 buffer solution containing benzoic acid and benzoate ion. What mass of benzoic acid and volume of 1 m NaOH is needed to produce this buffer solution? Molar mass of benzoic acid is 122.12 grams per mole. Molarity of sodium hydroxide is 1.00 mole per L. Ka equals 6.3 times 10 to the minus 5, and pK equals 4.20 for benzoic acid. The solution is that the ratio between base over acid is 2.00. Now we can rearrange since the volume is similar. Concentration of A minus equals 2.00 times concentration of HA, but will be expressed as moles. Like before, total moles equals 1.00 mole, and since desired molarity is 1 molar, total moles equals M times V equals 1.00 mole per L times 1 L equals 1.00 mole. This means that moles base plus moles acid equals 1.00 mole. If we sub moles base with 2.00 moles acid and solve for moles acid, it equals 0.333 moles, and therefore the moles base equals 0.666 moles. Note, this is the final amount of each component. We will use a stoichiometric table to determine working in reverse, given we started with 1.00 mole of just the acid, determine what amount of base was present. It turns out that there was 0.333 moles of base mixed with 1.00 moles of acid needed for this buffer mixture. Note, HA is benzoic acid and A minus is benzoate ion. Now, solving for the mass of benzoic acid and volume of sodium hydroxide is as follows. For benzoic acid, it required 122 grams of acid. For sodium hydroxide, it required 333 ml of base. Therefore, one will need 122 G of benzoic acid and mix with 333 ml of 1.00 m NaOH and dilute to a final volume of 1L with water to form the pH equals 4.50 Buckford solution. This example involves a weak base and added acid to prepare a Buckford. The question is, suppose I want to prepare a pH equals 9.50 Buckford solution containing aqueous ammonia, 6M, and ammonium ion. What volume of each component, 6M ammonia and 2M HCl, is needed to make 1L of a Buckford solution whose pH equals 9.50? For starters, it would help to know the molarity of the solutions. M equals 1 M equals 1 mole per liter for ammonia. M of hydrochloric acid equals 2 mole per liter. Kb equals 1.8 times 10 to the minus 5, and pKb equals 4.74 for ammonia, and pH equals 9.26 for ammonium ion. The solution is that the ratio between base over acid is 1.73. Now we can rearrange. Since the volume is similar, concentration of A minus equals 1.73 times the concentration of HA, but will be expressed as moles. Like before, total moles equals 1.00 moles, and since the desired molarity is 1M, total moles equals 1.00. This means that moles base plus moles acid equals 1.00 mole. If we sub moles base with 1.73 moles acid and solve for moles acid, it equals 0.366 moles, and therefore moles base equals 0.633 moles. Note, this is the final amount of each component. We will use a stoichiometric table in reverse, given we start with 1.00 moles of just the base, want to determine what amount of acid was present. It turns out that there was 1.00 moles of base mixed with 0.633 moles of hydrochloric acid needed to prepare this Buckford mixture. Note, Hb plus is ammonium ion and B is ammonia. Now, solving for the volume of each substance is as follows. For ammonium, it required 167 ml of base. For hydrochloric acid, it required 183 ml of acid. Therefore, one will need 167 ml of 6.00 m ammonia with 183 ml of 2.00 m HCl and diluted to 1L with water to make the pH equals 9.50 buffer solution. Here is a few exercises for you to work on. Suppose you have the following items in the lab. 6.0 m NaOH, 6.0 m HCl, citric acid, equals 192.12, K equals 7.4 times 10 to the minus 4, sodium citrate, equals 258.06, and lots of water. You have for equipment beakers in size of 50, 100, 150, 250, 400, 600, and 1000 ml. Volumetric flasks are available in size of 50, 100, 250, 500, and 1000 ml. A wash bottle for adding small amount of water along with stir bars are present, and a hot plate with stir is available for your convenience. Design a method on how to prepare 500 ml of a pH equals 3.0 buffer solution.